Our final note group for this unit has to do with mass and weight. Now, we've already taken a look at mass and weight when we looked at gravity, and this is just a review of that with one clarification added in now that we know Newton's laws of motion. So, we already know from Unit 1 and from looking at physical and chemical properties of matter that mass is a property of matter. Mass is how much matter you have. The quantity of matter that you have. It's measured in some type of SI unit like gram, kilogram, and measured on a triple beam balance. Weight, we know, is how gravity is, the force of gravity is pulling on your mass. So it is measured on a spring scale with a different SI unit, the Newton. So even though on the surface of the earth, because gravity is really affecting and pulling on everything here on earth, we tend to use mass and weight interchangeably, but technically they are not the same thing. Okay, and so you cannot use weight in newtons in an equation like Newton's second law that's asking you for a force. If it's asking you for a force, you need to know the weight of something. If it's asking you for the mass, then you need to put the mass in there. They're not they're not the same thing, even though we use them similarly here on planet Earth. So as we saw before, an astronaut very near the Earth is pulled by Earth's gravity. He has a certain amount of matter. He has 80 kilograms of matter, and so that is his mass. And near Earth, since gravity is pulling at 9.8 meters per second, his weight is about 800 newtons. If he's out in deep space where there is no gravity pulling upon him, he still has the same amount of matter, 80 kilograms, but now his weight is 0. He's weightless because gravity is not affecting him. And if you bring him near to the moon, where the pull of gravity is not as strong because the moon's mass is so much smaller than the Earth's, again, he still has the same amount of matter, unless he lobs off a leg or something, but his weight is much lighter, 130 newtons, because the pull of gravity is much less. So when we take a look at Newton's second law, the net force acting on something is equal to its mass times its acceleration, we can change this equation specifically to talk about weight. For example, if the force that we're talking about is your weight, because weight is a force. If you don't believe me, you've never had an older brother sit on you and, force you to confess something that you didn't do. Okay? Weight is a force. And you can use your weight to push something, pull something, change something's motion. So weight is measured in newtons. If the force that you're talking about is weight, then M stands for the mass of the object and A stands for the acceleration due to gravity. So I can rewrite this Newton's second law equation into a new equation that I can use to figure out the weight of something. Weight is equal to the mass of the object times the acceleration of gravity on that object. Okay, so we're going to practice taking a look at some weight problems and using weight as a force, or thinking about weight as a force rather than just as a property of matter, and use that force to move objects.